So again, as an experimentalist, I've tried to throw together a bunch of old stories with hopefully a perspective that's new to most, if not all of you, in an attempt to just provoke. I don't have any thesis I'm trying to defend. I have a number of ideas that I've found puzzling over the years, and I'm hoping people will have something to help me think about, or say about, and let me know as time starts to run along, and I can stop at any point as soon as we just discuss a lot of interesting questions. I first just wanted to put up 2 slides just showing who I am, what my group actually does in our day job, and then I'll begin by giving a brief reminder about weak values, in particular post-selective weak values. I wasn't sure in this audience. I know there are some people who know everything about them, some people who dislike them quite a lot, and there might be some people who just haven't thought about them very much. And in particular, what I want to do is talk about some ways in which these things seem to behave like probabilities and other ways in which they don't. And even something that I might call a derivation, although that word is perhaps a little bit over-strong, as in the case of Born's rule, which comes from classical probability theory, just to show again some of these seeming relationships between the two. And then I'll talk about a few paradoxes and experiments we've been doing with the perspective that a lot of these alleged paradoxes that we observed with post-selection, with weak measurement in particular, all seem to reduce to the same kind of probabilistic structure and can be traced back to something that looks almost like probabilities and then not quite, which I, as I said, find thought-provoking. And finally, a recent experiment of ours where we managed to make a photon act like 8 photons in a certain sense. I'll talk about. We were thinking about how you might model this classically, and I was a little bit surprised by some of what we found, and I wonder whether it points us to any of a deeper way of thinking about the meaning of these weak values. So first of all, this is my group. We have basically 2 halves, one where we study cold atoms. On the lower left, you'll notice the patented Canadian method for laser cooling. 2 of my students with a bucket of snow trying to see if that cooled lasers. We use Bose condensates and other cold atoms to study effects such as tunneling. On the right is a picture from a recent paper of ours about atoms tunneling through an optical barrier. On the upper left, what you're actually looking at is atoms impinging on a double barrier that acts sort of like a laser cavity for atoms. So you see some atoms transmitted to the right as you go downward in time. Apologies for the sort of experimental convention where time runs downward instead of upward, and some reflected to the left. But then this little spot in the middle actually indicates atoms being trapped in this resonant cavity, this Fabry-Perot cavity, which we found an exciting result. And the other half of my group works with photons, largely for studying quantum foundations, quantum information, and lately trying to make photons interact with each other, which is what I'll be telling you about, what Ghostbusters there was hinting at all those years ago. So the philosophical question that's been puzzling me for a long time is, what can we say about what a particle was doing before we observed it, right? In contrast to the textbook treatment of quantum mechanics, where we're told all we ever know is the wave function, which was given to us in the past, and changes as we observe it. And by way of motivation, this is the problem that originally got me interested in it. It dates back for me to my PhD thesis, but for other people to 1932, which is the question of how long a particle spends in a tunnel region, in a tunnel barrier. And this is meant to illustrate that poor hedgehog Heisenberg there, as he tunnels through the brick wall, is holding on to his pocket watch and trying to figure out what does it say when he gets through to the far side of the wall. And in particular, one of the controversies in the 90s was, can you ask how long the transmitted particle spends in the barrier as opposed to how long the reflected particle does? Or is a question about time spent in a region a question about the entire wave function, which does not commute with projectors onto transmitted or reflected wave functions? There were people arguing you cannot even ask this question. Whereas, coming back to dinosaurs, one of your favorite examples, I think the scientific tradition includes retrodiction, includes reasoning about the past based on current observations. And we should ask, when I see Heisenberg appear on the far side of the wall, what new information does that give me about his past? So that's what I find interesting about weak measurements or certain other things. Can we say something different about the different sub-ensembles, the reflected and the transmitted? So here's a simpler example that I often use to motivate it. It's stolen, as is almost everything, from Yakir and Orlev. This is a famous game that people use to fleece tourists in various cities around the world, where you hide something coin or a bill in one box or another and see if people can guess where it is. Of course, well, I was going to say, of course, we can only win this probabilistically, but in this context, I better even avoid saying that. I want to try to give you enough information that in a quantum mechanical sense, you can do this. So imagine the following variant of the game. Instead of putting my 20-pound note in one box or another, I'll put it in a quantum mechanical superposition, say A plus B. You, of course, can't tell me with certainty in which box this bill is, so I offer you additional information. I tell you that at some later point, I promise that I'm going to find this note in box B plus C over root 2, a different superposition. And this audience is too well educated for me to give you time to try to answer the question. I'll just tell you that I ask this question in many talks, and in general, when I ask it of physicists, what can you say about where the coin was, or the note was, between these two observations? Physicists are silent. But I've also used this example in audiences of general public with scientific interests, and they answer immediately, and they give the right answer. And to me, what's important about this is that it suggests that there's something lacking in our intuitions of what quantum states actually mean. So the right answer, by the appropriate definitions, is that it must have been in B. And if you replace these pluses with the word or, that becomes obvious. If I promise you that I'll put it in A or B, and that I'll find it in B or C, it obviously couldn't have been A, or I'd never have found it in B or C. It couldn't have been C because I only put it in A or B. And I think the general public is very quick, if they've heard of superpositions at all, to say, oh, plus is something like or. And it's disturbing that we are unsure on which occasions it's fair to do that and on which occasions it's not. But in testable senses, this really is the right answer, and therefore physicists ought to understand that's the case. That's the easy case. The case that's known as the three-box problem is a little more complicated. Suppose we put it in a superposition, equal superposition of all three boxes. But I promise you that we later find it in A plus B minus C, different superposition, with a finite overlap with that initial one. Well, it's very easy to see this, since there's really nothing different about a box or a superposition of boxes from a quantum mechanical perspective. What's important is that two orthogonal states, you can't prepare something in one state and find it in an orthogonal state. So that. And B plus C and B minus C are two orthogonal states. They might as well be different boxes. So I've prepared it in A plus what I'll call X prime, and I've found it in A plus Y prime, where X prime and Y prime are orthogonal. Therefore, it's easy to conclude it must have been in A, right? Just as in the previous case, where it must have been in B. Now, the problem with this is symmetry, because obviously I could equally well say A plus C and A minus C are two orthogonal boxes. So I've really prepared it in B plus X double prime and found it in B plus Y double prime, where X double prime and Y double prime are orthogonal. So I equally well conclude that it must have been in B. So there's a natural problem with this kind of retrodictive reasoning when it comes to quantum systems. And the question is, what should we then do? Should we discard all of this and say, that's what goes wrong when you try to implement retrodiction in quantum mechanics? Or can we actually learn how to think about this stuff?
What is wrong about saying A plus B plus C is orthogonal to A plus B minus C?
It's not.
No, it's not. Okay.
Other than that, it's fine.
Okay.
So, one way to think about what would happen in an experiment is to use the Holof-Bergman-Leibowitz rule, which is given down here, which basically just implements conditional probabilities in a quantum mechanical setting. It really is just Bayes' rule rewritten for quantum mechanics, and I won't go through the calculation, but these Q's represent the set of projectors and the measurement that we're doing. So if you ask, is the particle in A or not in A, it's a certain set of projectors, and you can work out that this conditional probability is 1. However, if you let the projectors be B or not B, then the probability of it being in B also works out to 1. In other words, if you do the first measurement, the probability of A, given the successful post-selection, is 100%. But if you do the second measurement, then the probability of B, given the successful post-selection, is 100%. And Yakir and Lev extended this to a case of n shutters to make it very provocative, and they pointed out that if you have, n slits, I should have said, if you have n slits that light could go through, and you have a single shutter, but you put the shutter in the right superposition of all the slits, and then you post-select it in the right superposition of all the slits, such that these weak-valued probabilities, let me call them for now, go to 1 in front of many of the slits. A photon sent at any one of those slits is guaranteed to be blocked. And in fact, a photon sent to any superposition of those slits is guaranteed to be blocked. On those occasions when the post-selection works. This experiment was recently done by Ryo Okamoto and Shige Takeuchi, published over here. The experiment looks something like that. I won't try to lead you through that diagram because I've forgotten exactly how most of it works. But if you think about what's going on, and we revert to the normal time ordering, imagine sending a photon to shutter B and asking whether or not it gets through. Well, if it gets through, then that means you've discovered that the shutter was not blocking slit B. So you've projected your initial A plus B plus C onto A plus C. A plus C, however, is orthogonal to A plus B minus C. And therefore, once you do this, once your photon gets through that slit, the post-selection cannot succeed. So it's natural that the conditional probability will now go to 1 of the particle being blocked, because whenever it's not blocked, your post-selection can't work. And the same argument works with A, of course. If you send the photon to A instead of to B, then finding the photon transmitted projects you onto B plus C, which is also orthogonal to A plus B minus C. But you have disturbed the state by making that measurement, right? That's the important point. So at this earlier time, when you test whether or not the shutter is in one position, you've changed it. You can't do both of those measurements. And in particular, if you look at the structure of this ABL formula, what you see in the denominator is something that doesn't depend just on the two states A and B, but on this set of Q sub j's, the possible projectors. In other words, the probability of a given projector, the conditional probability in this sense, depends on the full set of projectors in the measurement that you're doing. So the probability of A, if I measure is it A or not A, need not be the same as the probability of A if I measure is it A, is it B, or is it C. All right, the kind of measurement you do has really disturbed the state. So in that sense, I'm hesitant to call these probabilities properties of the system itself at the intermediate time. They're properties of the system given the measurement that I've chosen to do. Okay? So it would be nice to get past that. If it's just this measurement that's disturbing the particle, can we do anything without that disturbance? Does it make sense to ask, are the particles definitely in A or definitely in B if I don't have a particular choice of a set of projectors? So this was the motivation, or at least my understanding of the motivation for weak measurements. We prepare some system in an initial state I. We're going to find it later in F. We want to ask about some observable A at intermediate times. And you could ask whether it depends only on I, as in a naive reading of textbooks, or on F, or equally on both. You should expect that from the time reversibility of the Schrödinger equation, it would depend equally on both, as long as there is none of this, metaphysical, uncontrollable, irreversible disturbance that is supposed to be involved in measurement. So if you look at that ABL rule, you see that it is symmetric in a certain way, but in an almost classical way. And if instead we let this coupling to a measurement device, this attempt to glean information about A, be very weak, then we can ask, what would we have found? How big would the effect on a measurement device have been if we were not disturbing the particle very much? That's the idea of weak measurement. So here's the kind of scheme with cartoons, thanks to some nice artists at Physics World, where we have two systems. We have the wave function indicated in green there, and a pointer. But in order to make this measurement weak, not to get too much information to overly disturb the system, we let the pointer, indicated as a little stopwatch with a red arrow, be in a hugely uncertain state, so that on no individual occasion will we strongly entangle the wave function of the pointer, will we disturb the wave function much through the back action. So after this interaction, when we think we've not disturbed the wave function, we can go ahead and do a post-selection that we've chosen. For instance, we can say we're interested in the transmitted particles, not the reflected ones, in my earlier example. So we do a strong projection of that wave function onto the green or the red wave packet, and we say I only care about the green one. If it comes up red, I throw out my pointer. But if it comes up green, I look at where the pointer is, and it's pointing somewhat more or less random. It had a huge uncertainty to begin with. And some people stop here and say, well, that's not what my textbook told me measurement is. And this always disturbs me because I think those are people who failed their undergraduate laboratory courses. This is what measurement is. We always do uncertain measurements. We always average many of them, and we use the statistics to draw conclusions. So we repeat this millions or billions of times. Each time we get a different position for the pointer. That develops a histogram. And we look at the peak of the histogram, and we say, look, on average, the pointer has shifted by some amount. And that's what our theory ought to describe, the average effect of the system on things with which it interacts, measuring devices or other. And we can calculate what the shift of that peak is, and that's a straightforward quantum mechanics calculation. And this is what's known as the weak value, and that's the formula there, which is nice in some ways. It looks related to normal expectation values, right? It's an operator sandwiched between things, but it's symmetrically sandwiched between the initial and the final states, and renormalized in this funny way. So that's the quantity whose properties I want to be thinking about. And I apologize for the ancient slide that I dug up. I no longer talk about this very much, so my last slide on it is handwritten from the days of acetate transparencies. But just a few of the interesting properties are that that formula can easily be outside the spectrum of A. One example is that if you let the overlap f dot I, the denominator, get very close to 0, then the expression can diverge. It can actually be complex. It can do all sorts of nasty things. But it has some extremely nice properties. And one of them is that if I prepare a system in an eigenstate of A, the weak value is guaranteed to be that eigenvalue. If I already knew what A was, then that tells me the effect on a final system, on a coupled system. Fascinatingly, the same is true if I find it in an eigenstate of A. So I get just as much information from learning what S sub z was in my post-selection as I do in the preparation. Either one of those is enough to tell me what the value of this coupling would be. And since the expression is also linear, which might not shock you too much, the same is true for normal expectation values, but combining those two facts is very interesting because it means that even if I have two different operators that don't commute, but I know the value of one of them because of my preparation and I know the value of the other because of my post-selection, this linear formula allows me to make predictions about the coupling to their sum based on those two bits of non-commuting information. And they also obey other funny formulas, such as a kind of chain rule that's similar to chain rules for joint or conditional probabilities in classical probability, and so on and so forth. So I mentioned this business about two commuting operators. And one example of that is related to the first paper on weak measurements. It may seem a little less dramatic here, but if I prepare a particle with a spin of plus 1/2 in the x direction, and I post-select it with a spin 1/2 in the z direction, then Sx plus Sz has a weak value of 1, which means that there is another spin projector, Sz plus Sx on root 2, which has a weak value of 1 over root 2, which is outside the spectrum already. Right, the example was 100 in the original paper, but that's basically where it comes from. Something else that I find interesting is that there are plenty of things that we think of as intuitive, but are scared to say aloud in quantum mechanics. We suspect that we might be wrong if we pronounce them. And one of them is just a question about trajectories. Suppose that I have a particle that gets through a slit at some position x naught at time t naught, and I later find it to get through another slit, position x1 at time t1. Classically, I'd say, well, I know roughly what its velocity is, right? It was x1 minus x naught on t1 minus t naught. It's straightforward. Quantum mechanically, especially as the slit gets narrow, people would tend to say, I don't know about the people in this room, but people trained with the standard textbooks, I think would tend to say, well, no, the momentum became uncertain after you measured that first position, and it was going all over the place. And then you got lucky and it got through the second slit. But we can't conclude anything about the prior momentum from the fact that it got through that slit. Well, if you ask what the momentum was through this formalism of weak measurement, in other words, you imagine an operational approach where momentum was being weakly coupled to something else, and you ask what effect did this system have on another real system, then, in the limit of making the slits narrow, you can't do this for delta functions, the answer is exactly what you'd expect classically. So I think it's nice to see that there are things we can add to the standard way of thinking about the meaning of the quantum state, and they accord with intuitions that you might have had. But they're statements about real-world things. And when we ask, what does it mean to say what the momentum is, I think a lot of us have gotten too tied up in the formalism, what it means about certain operators and so forth. And I think that history is the other way around, right? We ask, how do systems affect each other? We come up with a formalism to describe how they affect each other. And if one system affects another as though it had a momentum of 2, then that really is what we mean. We say that we measured its momentum and it was 2. We shouldn't say it doesn't look like my favorite undergraduate textbook, therefore I refuse to call it a measurement. So my argument here was we should go back to that 3-box problem and ask, what can we conclude about these different boxes if we don't disturb the particle? And what I want to test here is that we had some classical intuitions that, if you prepare A plus B and you find B plus C, it must be in B. And we took those intuitions but combined them with quantum superpositions. We got into an uncomfortable situation. What should we do about that? Did we go wrong or not? Well, it turns out if you take this formula and you ask, what if I tried to measure whether or not the particle was in box A? In other words, I coupled to a projector onto A. That's something that would give me the expectation value, the expectation value of that operator would normally give me the probability that the particle is in A. So if we didn't have any post-selection, I think we'd all, well, I don't know about the philosophers, the physicists, I think would all accept that as a definition of a probability. The question now is, what if we do that same thing in a post-selective sense? We measure the thing, measuring which traditionally tells us probability, and we do it when a post-selection succeeds. We do, in fact, get a probability of 1 for the particle being in A or the particle being in B, which is now a little disturbing because we have these quantities that are supposed to be linear, and of course the probability that the particle is somewhere had better be 100%. And the way one gets out of that is if you do the calculation for box C, you find that this weak value turns out to be -1. And that's how some rule is preserved. And this is indicative of what I'm going to keep coming back to. This is what happens in many of these weak value paradoxes, that everything you would have liked for classical probabilities or other such quantities and feared you were going to have to give up in quantum mechanics remains valid, except for the idea that these quantities should be real numbers bounded by 0 and 1. So many people attack me for even using the word probability, and I grant you, this is obviously not a probability in the normal sense. It is obviously not a frequency or not even predictive of a frequency. And if I use the word, it's in part intentionally to provoke. These are things that behave like probabilities in some ways, and I would like to know whether that is pointing us towards anything else. I've also never really heard a better word. The first time I said this in front of Yakira, he got very angry, and he basically blamed me for all of the communities that dislike weak measurement, and saying, it's thanks to people like you saying negative probabilities that everyone hates us. And I said, well, tell me what I should say instead.
And limits like time in relativity.
Well, or a lot of people say it's like a Wigner function. There are other examples of quasi-probabilities where it's useful to generalize probabilities to accept negative numbers. But then we should ask what they mean. Yakir said, I believe that it's a positive probability for the negative presence of a particle, if I'm getting the word order correct. And although Lev sometimes uses similar words, I still have no idea what that's supposed to mean. So let's just go on and think experimentally about what these things would imply.
Weak value of projection operator.
Yeah, no. Obviously, we can just use the terms to describe exactly what we're doing operationally or mathematically, and that's fine. So can this be observed, or is there a sense in which the particles really were all in A or all in B? And as I said, Okamoto and Takeuchi did the strong measurement experiment. Kevin Resch, Jeff Lundin, and I long ago did the weak measurement in a purely classical setting. But it's instructive, I think, to think about how this works. In this case, we're just sending what, for the sake of referees, I call an ensemble of identically prepared single photons, but that just means a laser pointer. And I send it into an interferometer, which has 3 arms, which are 3 boxes. And we do a post-selection, which is we look at one of the 3 output ports of the interferometer, which is adjusted to project onto A plus B minus C. And now along the way, we can imagine measuring weakly whether a photon was in one path or another. And that's what these 3 glass plates labeled GPA, GPB, and GPC are meant to do. This is roughly an idea stolen from the very first weak measurement experiment, which was due to Randy Hewlett's group. And the idea is that you can use another degree of freedom of the photon, say its transverse position, as a probe of whether or not it was in a given path. If you send it through a tilted flat of glass, that shifts the beam by a small amount. If it shifts it by an amount small compared to the width of the beam itself, that means that every photon's position is being changed on average by an amount less than the photon's own uncertainty in position. So we tilt a flat in one arm or the other, and we know if the photon had gone through that path, it would on average have been shifted by whatever that is, 1 millimeter. If it had gone through a different path, it would not be shifted at all. Let's ask how big the shift is on the beam that we post-select, which went through some superposition of paths. And the answer, I've not even bothered to show you the data because you know where I'm going. It is 100% if I shift the glass in A or B. It is minus 100% if I shift the glass in C. In other words, the post-selected spot shifts in the wrong direction. And that's all a negative weak value really means. The effect on the pointer has the opposite sign from what you would have expected classically. However, since this case is classical, we can understand where it comes from. Of course, it comes from interference, but it's interesting to look at. I've got 3 spots that are superposed at a final beam splitter. The third one out of phase, so on the right there you see A plus B minus C. And that gives me a spot at the origin. What happens if I shift A to the right 1 millimeter? Well, B plus C are still perfectly superposed and out of phase. They interfere destructively. So all I'm left with is A. No matter how far I shift it, I get the full shift of A. And yet, if I shift B instead, A and C are superposed and interfere destructively. And I'm left with the full spot of B, the full shift of B. So there's nothing surprising about this classically. And yet, if you interpret it as a measurement, it's a little strange. It seems that every photon gets the full effect of either glass plate A or glass plate B. If you take this to true quantum experiments, by which I mean have the pointer held in a distinct system, then it's still just interference. Nothing has changed in the math, but it's harder to have a straightforward classical picture of because it's now interference of a many-particle system. But it's the same mathematical structure. And of course, C, for similar reasons, shifts in the opposite. I just want to say, if we think again about these probabilities, our problem was it was 100% in A and 100% in B, and I thought that violated some axiom of probability theory. And it does, in that it cannot be in A and B at the same time. And if you try to fill out this little table, and you say, well, on the bottom there, it was definitely in A, which is the sum of A and B and A and not B. And it was definitely in B, but it couldn't have been in A and B at the same time. You're still able to fill out a probability table that adds up to 1, but only by allowing a negative probability. So these things that we think of as product rules for probability, if A is definite and B is definite, then A and B must also be true. To prove that, you need to assume, which we always do, that probabilities can't be negative. Once you drop that, then everything else is allowed. I don't really know what that resolves, but tables like this seem to be at the heart of essentially all of the surprising predictions that we experimentalists like to test for weak values. So I'll show you a few other examples afterwards. But I wanted to draw the connection with probabilities from a different direction as well, and say, suppose no one had done this calculation of the weak value. No one had thought to use quantum mechanics and predict what is the shift of the pointer. And instead, suppose I know something about conditional probabilities classically, and I just tried blithely to extend that to the quantum realm. So I begin with a sense of probabilities. All right, I want to know about expectation values, but that's fine. An expectation value is just a weighted average of eigenvalues, right? The sum on J of Aj, P of J. But if I've now prepared a system in I and post-selected it in F, I want to replace those probabilities with these conditional probabilities. What's the probability of eigenvalue J given my preparation and my post-selection? So we'll take Bayes' rule as the way to do this. And we'll again take this definition that quantum mechanically, when I say P of A, I mean the expectation value of a projector onto A.
It's just the definition of conditional probability. It's not Bayes' rule.
Yes, that's right, classically. And now I'm just asking how to extend it to.
Okay, that's not Bayes' rule.
Sorry, I left out right one term in the numerator. Okay, that's right. And now comes the one place where we just have to put something in by hand. which is to ask, what does it mean to talk about a joint probability quantum mechanically? If I want to know the probability of A and B, each of which was represented by a projector, it seems natural to just multiply them, and multiply them with the correct time ordering if we know quantum mechanics. So where we have those joint probabilities, we'll just replace it with that expression on the lower right, psi b, b, a, psi. And if you go through a few steps of math, I don't think there's any point in leading you through them slowly, this reasoning immediately gives you, as the conditional expectation value for A, the weak value formula. Now, I can't really justify that step in the middle. It seems natural, that it's not something one can prove rigorously. And I continue to find it provocative that if you take this simple-minded approach, you happen to get the answer that agrees with the calculation of what should really occur experimentally. Maybe it's one of these coincidences where there just aren't that many symmetric quantities of the right form that can be written down, and I shouldn't be surprised. I don't know, but it's one more way in which these weak values seem to me very closely tied to basic ideas of probability theory, where certain axioms have to get modified. Finally, there was this one experiment we did recently that got us thinking about a completely different context of probability. And for me, this relates to the question of whether or not we should think of these weak values as telling us something about an ontological reality beyond the wave function that we initially had, which I think is an open question. In our experiment, we were trying, for other reasons, semi-practical reasons, to measure the number of photons, to use an interaction between two light waves so that one light wave could act as a pointer and count the number of photons in another. This would be useful for quantum computing, for instance. So we have a probe beam, and we have, let's say, a single photon source, and the single photon is indicated in red. I'm lying a little bit. We didn't actually do this yet with a true single photon, but the details maybe don't matter for the purpose of this discussion. That photon can go through path A or path B. And in path B, we let it go through our atom cloud where some interesting physics occurs, so that if it goes through that path, it writes a phase shift on this blue probe beam, which we detect in an interferometric way. So the bottom line is just, we can do a measurement on that probe that should have a signature of the number of photons that were in path B, which should be 0 or 1, because we're imagining sending in one photon. But now let's do this in a post-selective sense. Let's prepare our initial photon in A minus B over root 2. That's what a beam splitter does if you have the appropriate phase. But let's post-select it in RA plus TB, simply by having another beam splitter and then that green photodetector that fires when the photon comes out a particular output port of the interferometer. So when that green detector fires, I want to ask, what did the probe see? Was the photon in A or B or half and half when that detector fired? Now, if R and T were 1 on root 2, that detector would just never fire. So let's let them be slightly different from 1 on root 2, 0.5 plus or minus delta, and you can work it out. And what you find is the denominator gets very small. The probability of the detector firing is very small if I have almost perfect destructive interference. And when that denominator gets small, the weak value diverges, and I can get an arbitrarily large weak value for this number of photons in path B. Even though I only sent in one photon, that weak value, so the effect this system would have on my probe, could be arbitrarily large. And we did the experiment. It looks in cartoon form something like this, but again, I don't think the details matter to this audience, but there's data that off on the right is the single photon phase shift, and as we make delta smaller and smaller, you see these points go up to as much as 8 times the single photon phase shift. So we really are seeing one photon act, in some sense, as though it were many more than one photon. And the question in my mind is what does this really mean? I mean, there's no problem about the math. We can understand this. It is another interference effect like those 3 spots. But does it tell us something about what the photon is doing? Is there any real sense in which I should think the photon number was something like 8 in there? Or is that just a misleading way of thinking about these measurements? So, due in part to a fight with referees, we started thinking a lot about that. And I started thinking of different models that might be similar. For instance, if we hadn't done this with a very quiet laser source, but had done this with a laser that was known to be really, really noisy, we just weren't sure how intense it was, Then it turns out whenever you see a post-selection, you would gain extra information. You'd realize that, oh, the laser was probably brighter at that instant than at other instants because I saw a photon, and photons are rare. And you could draw classical probabilistic conclusions in that case. But I wanted to come somewhere in between. So we started thinking about what Ed Janes used to call a neoclassical model for optics. This was part of a long argument about whether you needed quantum mechanics or not to understand quantum electrodynamics and things like the lamp shift. And James was trying to come up with a model which dispensed with it. And the basic postulate is maybe optics, electromagnetism is classical. But based on observations, there is some additional noise field permeating the universe. And the thing that we would call vacuum fluctuations as quantum physicists become just another hypothesis. For some reason that we don't know, there's a law of physics that there is, h bar omega on 2 of extra energy and fluctuations all around in every mode. So we'll take a classical view of an interferometer where a field E naught splits at a beam splitter into E naught on root 2 and E naught on root 2 deterministically, to one in which there were also some fluctuations, so that instead of exactly E naught on root 2, we have a field interacting with our atom, which is fluctuating around that value. And then ask, if that's a real fluctuation, when a detector fires, what information do we gain? So we went through this calculation just to see whether such a model was possible. And the calculation is simple. We've got some probability distribution shown in blue for E1, and it's peaked at E naught on root 2. And we have some green curve that shows the destructive interference. There's some value of E1 for which no photons would reach the detector. At E naught over root 2, some of them reach the detector, but there are other values at which even more photons reach the detector. So that's that green quadratic curve around the destructive interference point. And if you want to update your probability, the blue curve, given your observation of a detector firing, you just multiply these two things and renormalize. And of course, if you multiply that Gaussian by this growing quadratic, you shift its peak to the right, and you get the red curve you find when the detector fires. My conclusion for such a classical model should be that the field was a little larger on that occasion than its average value E naught on root 2. So we worked out, what does that mean in terms of energy? What is E naught squared? And the answer was it's exactly what's predicted by the weak values. If you believed this kind of classical model of the world, then you would say, yes, your detector will fire sometimes. And when it fires, your best prediction of E naught really is equivalent to the field of 8 photons. That's really what it was on those occasions, on average. So if you believe that field strength is an element of reality, and I don't necessarily believe that, then you would take these weak value predictions to be teaching us about that reality. So the open question for me is, well, maybe that's not the right element of reality. Maybe there are some other elements of reality. But perhaps these weak values are still teaching us about them. Because the other option is to say, when you have classical noise, this formula and your experiment are correctly telling me how to update my knowledge of that classical fluctuating parameter. And when you have quantum noise, the same formula is valid and it still describes your experiment, but you shouldn't think of it as telling you about reality anymore. And that happens in a continuous way, which would seem a little bit shocking to me. I'm being a little bit misleading, because if you look at this curve as a function of delta, that black dashed line is the weak value prediction, and the solid curves are actually these Jamesian predictions, depending on the strength of the field you send in. So you notice there's a region in which they agree pretty closely, certainly to within our experimental error. But for any particular value of the field, there is some delta small enough that these would, in fact, deviate from one another. And we've not yet tested that regime. So I think that was the main point I wanted to make there, but I did just promise to show you, skip some of this stuff, Lucian's famous paradox, but I just wanted to get to the point of these truth tables. If you ask yourself, what can weak measurement tell us about other kinds of red prediction, like in this bomb experiment and the concomitant paradox, you find again that it comes down to a problem of probabilities. If we conclude, in Lucian's case, that an electron and a positron were both in an interaction region, but they must not have both been in the interaction region since they didn't annihilate. So we know the probability of the electron being in is 1, the probability of the positron being in is 1, and yet somehow the probability of them both having been in must have been 0. that seemed initially like a contradiction. Again, in the context of weak values, it's not. These two off-diagonal probabilities must be 1, and that's fine as long as we accept a -1 here. And these, again, are the weak value predictions. So red prediction becomes perfectly legal as long as these things that used to be probabilities are now allowed to be negative. If you go to other cases that people have been thinking about, like this apparent violation of the pigeonhole principle, where you can have 3 pigeons in 2 boxes and yet never find 2 pigeons in the same box. Let's focus on pigeons A and B, holes 1 and 2. It turns out the probabilities, the weak value projectors, look something like this. They add up to 1. The interesting thing is there's a non-zero, although imaginary, weak value for them both to be in hole 1, and a non-zero, but imaginary, weak value for them both to be in hole 2. If you measured, are they both in hole 1, you might find yes. But if you can implement the measurement that just says, are they in the same hole? I'm agnostic as to which. Then you get 0, because the sum of those two things is 0. And that's the entire paradox. The Cheshire Cat paradox that people were so excited about, and the interpreter saying, oh look, all of the mass of the particle is in arm 1, but all the charge, I said charge, it's a more interesting application, but I should have said spin, but all the spin is in arm 2. Really, if you just ask, what is the probability of a spin-up particle in arm 1 or arm 2? What's the probability of a spin-down particle in arm 1 or arm 2? This is the truth table. You have 1/2, 1/2, 1/2, minus 1/2. And if I ask, how many particles are in arm 1? Well, I should add the number of spin-ups and spin-downs. So I get 1 on the left and 0 on the right. But if I ask, what is the angular momentum contained in arm 1 or arm 2? Well, I should take up minus down, shouldn't I? So the spin is n up minus n down, and that's 0 on the left and 1 on the right. But it all really just comes down to these same funny truth tables, where things we're used to thinking of as positive can be negative, or sometimes even imaginary or complex. And somehow the fact that so many of these paradoxes really just always reduce to that same structure is one of these things that I continue to find provocative. So I could tell you about planned tunneling experiments, but I've been talking too long and would be more interested in hearing comments and criticisms and things like that. So I'll just leave you with this summary of some of the things that we've been thinking about.